When a nonlinear shock hits a modern macroeconomic system, the flat, two-dimensional grids we use to model it often collapse. The static relationships mapped in those spreadsheets shatter under the weight of compounding, unpredictable variables. Today's global economy operates on hyperconnectivity. It is bound by a strict triple constraint: inflation management, debt sustainability, and labor market stability. Pulling a lever to stabilize one almost always destabilizes the others. The central bankers and fiscal planners tasked with navigating these constraints process a massive, high-velocity stream of daily indicators. Yet the operational interfaces they rely on remain tethered to the flat-screen design logic of the late 20th century. Scrolling through dense reports and static dashboards requires immense mental conversion, stripping the data of its spatial relationship and inducing severe cognitive overload. Decades-old computable general equilibrium models have served as the gold standard for testing policy. But in real-time execution, their computational opacity creates a black box. Policymakers can read the output, but they cannot physically observe the systemic risks accumulating beneath the surface. The Sovereign Policy Mesh, or SPM, discards the traditional dashboard interface entirely in favor of an immersive, spatial computing environment. It transitions the user away from analytic observation, reading a screen, and toward direct, immersive manipulation. To make this interaction mathematically rigorous, the SPM is built on a framework known as Interactive Computable General Equilibrium, or ICGE. This animated diagram maps out how the system visualizes the economy. Instead of rows and columns, the framework generates a spatial network of interconnected neural nodes. Causality vectors directly link policy hubs, like monetary rates and consumer prices, in three-dimensional space. Within this mesh, abstract policy levers cease to be text fields. They are rendered as physical 3D objects that the user can directly manipulate with their hands. By utilizing spatial computing, the system bridges the representational gap. The SPM treats high-velocity data and the physical intent of the policymaker as a single interactive input. To understand how intent is processed, we have to isolate the architecture of a single neural node, such as inflation. This diagram shows the internal physics of a node. It is not a solid object. Using WebGL, the system models each economic sector as a high-density particle swarm. The visual behavior of this swarm is driven entirely by data. Its density and baseline vibration frequency are tied directly to current market indicators. To calculate the final frequency of the node, the engine adds a historical volatility component, represented by sigma, to that baseline rate. If a specific sector is experiencing extreme historical volatility, that high sigma value causes the entire geometry of the node to visibly shake. This ambient vibration delivers what researchers call affective intelligence. Long before a policymaker checks a specific percentage, they can physically sense the tension and instability radiating from a stressed sector. Engaging with these nodes requires tracking the user's physical agency within the digital space. The hardware utilizes continuous skeletal tracking, identifying 21 distinct landmarks on the user's hand to read spatial affordances without the need for traditional menus. This diagram demonstrates the system's core trigger, the sovereign pinch. When the distance between the user's thumb and index finger drops below 30 millimeters, a persistent neural link locking on to the target node. Once locked, the user performs a policy injection by physically pulling the node up or down along its local y-axis. The engine continuously calculates this vertical displacement, measuring the physical distance between the node's current coordinate and its initial position. That physical distance is then multiplied by a calibrated sensitivity constant, known as kappa, to output a precise policy modulation magnitude. The cognitive load of typing variables into a legacy interface is removed. Executing a 50 basis point rate hike now becomes a fluid, visceral pull directly on the glowing fabric of the macroeconomic simulation. Stepping back to view the broader mesh reveals the consequences of that single physical gesture. Pulling one node forces the network to react. The injection immediately triggers nonlinear secondary and tertiary ripples that cascade across connected sectors. To guarantee these spatial ripples behave accurately, the system's logic is anchored in 50 years of Federal Reserve economic data, or FRED. This massive longitudinal corpus holds all the critical empirical records of cyclical volatility, historic market crises, and real-world recovery trajectories. The SPM engine extracts a precise 4x4 coupling matrix directly from this 50-year dataset. This matrix visualizes the causality vectors between different hubs. It relies on historical elasticities, mapped here as beta variables, to define exactly how sensitive an equities node should be to a change in an interest rate node. When a user performs an injection, the engine multiplies the magnitude of that initial gesture by the specific historical elasticity of the connected node. It then integrates a stochastic volatility component over time, ensuring the resulting ripple organically accelerates and decays. The shifting layout of the mesh is a strict mathematical simulation. Every visual reaction is constrained by 5 decades of recorded market sensitivity. Individual node interactions ultimately feed into the system's primary diagnostic function, assessing the aggregate health of the entire macroeconomy. As the mesh contorts from multiple policy injections, the engine continually calculates a variable known as systemic stress. This calculation models the equilibrium bar. It generates a master systemic stress score that updates in real time with every physical adjustment the user makes. The formula computes the weighted sum of every node in the mesh, measuring how far each one is deviating from its 50-year historical stability corridor. The engine constantly checks this total stress score against a predefined safety threshold. If the combined policies create a recessionary or crisis-prone mix, the score breaches the threshold, triggering the perimeter of the heads-up display to pulse red in a critical warning state. This visual safeguard provides instant feedback, alerting policymakers to a recessionary mix before the decision is codified into law. As decision support systems evolve, the core mandate of the industry is to achieve human-centered AI, environments where the computational heavy lifting enhances rather than replaces human agency. Two-dimensional dashboards positioned the policymaker as a passive observer. The sovereign policy mesh makes them an active participant, relying on spatial intuition and physical command. The immediate roadmap for the system involves integrating live API feeds, upgrading the mesh from a localized historical modeling environment into a real-time sovereign war room. By combining the empirical rigor of ICGE data with the spatial mechanics of modern physical engines, the mesh establishes a visceral, tactile standard for executive economic management.